we know that voltage is negative and positive charges. And if it's large enough, it can cause electrons to move through air and insulate. We also know what can happen when a wire is connected between two charges. Watch. In these examples, the reactions occur due to a tremendous number of electrons moving from one charge to another. This movement of electrons is called current flow. In this lesson, we'll show you a few things about current. But before we get into the subject, let's review a few facts that we've already talked about. For example, in the discussion of voltage, we showed some methods of creating negative and positive charges. The car battery was an example of creating a voltage by chemical means. Remember, the electrolyte of the battery reacts with two metals, causing one to gain electrons, the other to lose electrons. Or one becomes a negative charge, the other a positive charge. Now, if I connect a bulb across the charges, like this, the bulb will light. We've used the voltage of the battery to do some work. But what causes the bulb to light? Well, remember, this material contains an excess of electrons. This one a deficiency. If a suitable path is provided, electrons will leave the negative charge, travel to the positive charge, and try to neutralize it. So it's the movement of electrons caused by the voltage that lights the bulb. The pressure causes current flow. But how do we know that electrons are moving between the two charges? Well, under the right circumstances, we can see it. We've said that this device develops a tremendous voltage, so much that it will cause electrons to travel through air. Now, electrons are solid particles, so if they're moving between these rods, we should be able to detect them. To detect them, I'll use this paper. I'll pass it between the rod and the arc. Now, if we have solid particles moving between the rods, they should penetrate the paper. Let me turn it on, and we'll see what happens. Get the arc going real good. And I'll pass the paper through the arc. Do it several times. Now, I'm moving the paper very fast because if I don't, the arc would burn it up. Okay, that should be enough. Now, I'm going to use a light behind the paper, and we'll see what happens. Okay, let's take a close look at the paper then. There's a nice hole, a big one right there. There are some nice holes. Holes all over the paper. Holes created by electrons moving between two charges. Then the holes were actually caused by solid particles penetrating the paper. In the case just a moment ago, then, our bulb glows due to a movement of electrons, due to a movement of electrons through the filaments of the bulb. Now remember, this movement of electrons is called current, and current does the work in electricity and also in electronics. Now, since current does the work, it's important that we know the conditions required to have it. Well, the first requirement for current is pretty obvious. For example, current causes this radio to produce sound until I remove the voltage. When I remove the voltage, no sound. Apply it again. We have sound. Also, current will cause this light bulb to light. Let's try this ordinary AC outlet, and I'll plug the light bulb in. Applying the voltage to the bulb, if I can find the socket. There it is. Voltage causes the bulb to light. If I unplug it, no light. Now, in each of these cases, when the voltage was removed, current must have stopped because we no longer produce the desired work. Each time we reapplied the voltage, the current produced light and it produced sound. So to have current, it's obvious that one requirement is voltage. Now, the next requirement for current is also pretty obvious. For example, let's suppose that the object is to use current to light this bulb. Well, here's a voltage source. Here's a voltage source. They both provide current. The bulb is the device that uses the current. But how do we get the electrons from the source to the bulb? Let's try this one first. I'll connect the bulb to this rod like this. Let me move it up just a little bit to separate. Now, the other side of the bulb would be connected to this rod by the air separating the bulb and the rod. This means that the electrons must travel through air in order to flow through the bulb. Let me turn it on and we'll see what happens. The current lights the bulb. Or we could use these wires and this voltage source to get the electrons to the bulb. Again, the current lights the bulb. Let's consider what I've just done now. Here, we provided a path for current by using air, an insulator. And the voltage required to light the bulb is about 10,000 volts. In this case, I provided a path by using copper wire, a conductor. The voltage required about 115 volts. In each case, then, the bulb lights. But which is the most logical method? Well, I sure wouldn't want to rely on 10,000 volts to light the lights in my house. The arc could cause a fire. And I wouldn't want to use 10,000 volts in my radio, say, to provide voltage to my car radio. Naturally, it's this one, the one that uses 115 volts in conductors. So to have a practical current flow, insulators cannot be used. Now, let's pursue this idea just a little further. We've already seen that when a bulb is connected to a battery, electrons will flow from the battery through the wire, the bulb, and back to the other side of the battery. In this case, I'm using copper wire. And remember, copper allows electrons to flow because it has a large number of free electrons. Now, if I put an insulator in the circuit, the bulb doesn't glow. Here's the insulator, the air between here and the battery. Remember, an insulator contains few, if any, free electrons. It prevents current flow except when there's a tremendous amount of voltage. So another requirement for current is a complete path through which the electrons can flow. And keep in mind that if we generate a high enough voltage, current will flow through anything. But to keep the voltages in a practical range, we'll usually use conductors. Now, there are a few more facts about current that we should know. For example, what is the direction of current with respect to the voltage source? Well, we said that electrons move from negative to positive. But how do we know that this is true? Besides, what difference does it make? Let me show you the importance of knowing how current flows. Some devices will operate only when current is flowing in the proper direction. This semiconductor diode is such a device. Now, I'll make a connection here. Move the bulb in so we can see all of the action. Now, if I apply current to the device in the proper direction, like this, the bulb lights. If I turn the diode around and try to make current flow in the wrong direction, nothing happens. So to make this diode work, we would have to know the direction of current flow. Now, also, the design of some devices is such that if current is improperly applied, the device can be destroyed. Such a device is this one. Now, watch what happens when I try to force current through it in the wrong direction. Notice the smoke starting to pour out. The device could be destroyed. So to keep something like this from happening, you would have to know the direction of current. Okay, that's why we must know how current flows. Now, let's see if we can prove that it flows from negative to positive. In the next demonstration, I'm going to use this little device, the semiconductor diode that we've already seen. Now, you'll study this device in detail later on. For now, though, you should know that current will flow through it in only one direction. It works something like this check valve that's designed to control the flow of water. Here's how the control valve works. If I place it so that the arrow is in the direction of water flow, it'll let the water through. But when I turn it around so that the arrow is against the flow of water, it'll shut the water off. So let's try it in this demo. This is my water source, a pressurized source. The flow will be from here through this tube and into this container. Now, I'm using colored water so that you'll be able to see what's happening. So first, let me place the control valve so that the arrow is in the direction of flow. Now, when I turn the water on, it flows freely. Okay, I'll disconnect everything, drain it out, and I'll turn the control valve over. Now I'm placing it so that it's against the water flow. Now, watch what happens when I turn it on. It blocks the water flow. It shuts off the flow almost completely. Well, the diode will do basically the same thing. Very similar to this control valve. When the arrow is placed in the direction of flow, it'll let everything through. If you turn it around so that the arrow is against the flow, it will block it. The diode will do essentially the same thing to current. Remember, we said that current flows from negative to positive. That's in this direction. Now, I'm going to put the diode in the circuit so that the arrow is in this direction. It shouldn't affect current. Let me make the connection. The bulb lights, so there must be current through it. Now I'll turn the diode around so that the arrow is against this flow. Remember, if current flows from negative to positive, the arrow is against that, so it should block it. Let's see. Making the connection, the bulb doesn't light. So just as the control valve blocked the flow of water, this diode is blocking current. Now I'll turn it back around again. Current flows, and the bulb lights. So it should be obvious then from this little demonstration that current flows from negative to positive. Now remember, when I speak of current flowing from negative to positive, I'm referring to the current that flows outside the power source, or the current in the external circuit. Inside the power source, the battery in this case, current flows from positive to negative. Now this is a very important point, so be sure that you understand it, because later on you'll be using the current in this power source to calculate numerous things. So remember this. Current flows in a continuous path from negative to positive in the external circuit, and from positive to negative in the power source. Now, you should also remember that the requirements for current are a source of voltage and a continuous path through which current can flow. Here are some terms associated with current that you should become familiar with. For example, the symbol for current is the capital letter I. A coulomb. That's a measure of the amount of current. Now, 1 coulomb is this many electrons. Now, of course, trying to count this many electrons would be like trying to count the grains of sand on a beach. It just isn't practical. So we'll rely on meters later on to measure current in amperes. Now, an ampere is 1 coulomb flowing past a point for 1 second. And it's called ampere in honor of the French physicist who discovered this means of measuring current. Now, remember also that current is the movement of electrons. It will cause a bulb to give off light. It will cause a radio to produce sound. It's the force that does the work in radar, computers, and communication. We've seen that when a conductor is placed across a voltage, the voltage will cause too much current to flow and burn up the wire. On the other hand, if an insulator is used, very high and dangerous voltage is required to cause any current. In the next lesson, we'll talk about a happy medium. Example of creating a voltage by chemical means. Remember, the electrolyte of the battery reacts with two metals, causing one to gain electrons, the other to lose electrons, or one becomes a negative charge, the other a positive charge. Now, if I connect a bulb across the charges, like this, the bulb to a tremendous number of electrons moving from one charge to another. This movement of electrons is called current flow. In this lesson, we'll show you a few things about current. But before we get into the subject, let's review a few facts that we've already talked about. For example, in the discussion of voltage, we showed some methods of creating negative and positive charges. The car battery was an example. We know that voltage is negative and positive charges. And if it's large enough, it can cause electrons to move through air and insulate. We also know what can happen when a wire is connected between two charges. Watch. In these examples, the reactions occur due to the bulb will light. We've used the voltage of the battery to do some work. But what causes the bulb to light? Well, remember, this material contains an excess of electrons. This one a deficiency. If a suitable path is provided, electrons will leave the negative charge, travel to the positive charge, and try to neutralize it. So it's the movement of electrons caused by the voltage that lights the bulb. The pressure causes current flow. But how do we know that electrons are moving between the two charges? Well, under the right circumstances, we can see it. We've said that this device develops a tremendous voltage, so much that it will cause electrons to travel through air. Now, electrons are solid particles, so if they're moving